Welcome back. We're continuing to look at indefinite integrals and reminding ourselves once again that although we had some basic integration rules, we didn't have a rule on there for products or quotients. So we have a product rule and a quotient rule for derivatives, but not for integration. There is in Math 101, the second calculus course, a section called Integration by Parts, which focuses on the product rule equivalent for integration. But for now, if you see something that's a product or a quotient, that means you're going to need to do something to it to get it into a form where you'll be able to find the indefinite integral. So, for example, the first one that I'm looking at, x plus 3x minus 7 multiplied together, for the indefinite integral there, I would have to actually carry out that multiplication. X plus 3 times x minus 7. If I were to multiply that, that would be x squared minus 4x minus 21. And now that I have it as an indefinite, now that I have it expanded, I can find the indefinite integral. X cubed over 3 minus 4x squared over 2 minus 21x plus our constant c, which we can simplify one step further. X cubed over 3 minus 2x squared minus 21x plus c. Second one, same sort of an idea. I'm going to first think about this as being this polynomial on the top. And it's divided by square root of x, or in other words, it's divided by x to the 1/2. So what I'll do is I'll imagine taking each and every one of those terms in the numerator and dividing by x to the 1/2. So x to the 5 divided by x to the 1/2, and same thing with the next term and the next term and the next term. So I'll do that sort of simplification. So x to the 5 divided by x to the 1/2 is x to the 9/2. X squared divided by x to the 1/2 is x to the 3/2. X to the 1 divided by x to the 1/2 is x to the 1/2. And then 2 divided by x to the 1/2 is 2x to the -1/2. There we go. So it's no longer written as a quotient, which means I can now go ahead and go term by term and use my integration rules that I know. So let's do that for this. So we'll have adding 1 to the power, then dividing by powers, we'll have x to the 11/2 divided by 11/2. We'll have 3x to the 5/2 divided by 5/2. We'll have minus 5x to the 3/2 divided by 3/2, and then 2x to the 1/2 divided by 1/2. And of course, plus our constant c. And then I can just clean that up one step further. So 2x to the 11/2 over 11. I'll have 6x to the 5/2 over 5. I'll have minus 10x to the 3/2 over 3. And then I'll have plus 4x to the 1/2 plus constant c. Okay, a couple more examples. So on the left side here, we have the indefinite integral of 3x plus 1 cubed. And later on, we're going to see a way to deal with such a thing. We're actually going to see towards the end of this chapter a technique of integration by substitution that would help for this specific case. But right now, we don't know substitution, so that means that on the side, we're going to need to actually multiply out what is 3x plus 1 all cubed. And of course, we know that that's not as simple as just cubing the 3x and cubing the 1. It's us doing all of the multiplying out of 3x plus 1 times itself. So I do it step by step. So when I multiply the first two brackets together, I've got 9x squared plus 6x plus 1. And then when I multiply the two brackets together, 27x cubed plus 18x squared plus 3x plus 9x squared plus 6x plus 1, which gives me 27x cubed, 27x squared, 9x, and 1. So I did all that multiplying on the side, and now I'm ready to actually tackle the real problem, which is what's the indefinite integral of that? So my 3x plus 1 cubed, the indefinite integral of that is the same as the indefinite integral of that big polynomial, 27x cubed, 27x squared, 9x, and 1. And now we just go right ahead and use our power rule, adding 1 to the power, dividing by the power, adding 1 to the power, dividing by the power, and so on. And then the only thing really to do here is there's one term where I can clean things up a little bit. The 27/3 is the same thing as 9, and then that's kind of about it. All right. Now, of course, we've dealt with now all sorts of polynomial stuff and rational functions, but for trig functions, maybe it's not manipulating things algebraically. Maybe it's using some sort of a trig identity. So right now, if I'm looking at this, I can see a couple of things that are problematic. Number one, I have no idea what to do with a cosecant cubed. Number two, I've got a product of a sine times a cosecant cubed. I also don't know an antiderivative of tangent squared. So I'll need to do a few things just to get this into a shape where I can do something with it. The first thing that I'm going to note to myself is that sine and cosecant are reciprocals of each other. So when I say that I've got sine times cosecant cubed, I've got a sine times a cosecant times another couple of cosecants. And that one sine and one cosecant will cancel each other out. So that's at least something that makes it a little bit nicer for me. And the fact that I don't know what the antiderivative of tangent squared is isn't really a problem because I know I've got a Pythagorean identity that tangent squared is secant squared minus 1. So really, my indefinite integral that I was given simplifies to give me just antiderivative of cosecant squared plus secant squared minus 1. And that's easy enough to do. We know that an antiderivative for cosecant is squared is negative cotangent. For secant squared, it's tangent. And for 1, it's just x. And then, of course, plus our constant c. Okay, so let's do some more stuff here. And right away I can see with the e, I've got a quotient, which is kind of a problem. If it was just in e that the denominator was just u, then I would be in a simpler sort of situation like I was before with the second example, and I could just divide everybody individually by u, and that's easy enough to do. Since the denominator is a little polynomial, u minus 1, then I'm going to actually have to do some division on the side. So I guess I'm going to do, and you can do with this one either synthetic division or long division if you remember it. I always remember long division a little bit easier, so I'm going to do that. Remember that for whether it's synthetic division or long division, you have to have all of the powers of the variable accounted for. So I've got u cubes and u squareds, but I don't have any u's, so I need to put in a 0u. There we go. U goes into 4u cubed, 4u squared times. I multiply 4u squared times u and times negative 1. And now I'm going to subtract Negative 3u squared minus negative 4u squared is a positive 1u squared. And I'll bring down the next term and repeat. U goes into u squared, u times. We multiply. U times u is u squared. U times negative 1 is negative u. And I'll subtract. 0u minus negative 1u is 1u. And I'll bring down. And how lovely for me, everything goes in nicely and evenly. One time for the last. And there is no remainder. So actually, as it turns out, u minus 1 must have been a factor for my numerator, because when I divided u minus 1 into my numerator, it went in a bunch of times and left nothing behind. So actually, this simplifies to just be 4u squared plus u plus 1. And easy enough to do now. I'm just going to do my usual power rule business. And there we go. We have 4u cubed over 3 plus u squared over 2 plus u plus our constant c. Last one on the bottom, and this is one where I'm going to have to do a little bit of thinking about it. If I start thinking about the option of splitting things up, because again, I've got a quotient here, I could do the splitting things up and thinking of it as 1 over cosine squared plus a sine over cosine squared minus a sine cubed over a cosine squared. I could split it up into 3 terms that way. Some of it would be fine. 1 over cosine squared, that would be secant squared. I could deal with that. Sine divided by cosine squared, you could show that that's the same thing as secant times tangent, which again, that's fine. But then we run into a problem with that last bit, the sine cubed over cosine squared. That's not really anything nice. So I feel like although the idea of splitting things up into 3 terms rather than having one big fraction is a good idea, right now I don't think that's super helpful because that will leave us with a sine cubed that I'm not sure what to deal with. So here I have an idea instead of what I might want to do, and that's this. I know that sine cubed is the same thing as sine times sine squared. And I also know that sine squared could be written in terms of cosine squared using a Pythagorean identity. So that's kind of my idea here. I'm going to rephrase this. Instead of having sine cubed, I'm going to think of it as sine times sine squared, and sine squared is the same thing as 1 minus cosine squared. So this actually does some nice things for us, because if I do that, then now I have in the numerator, I'll have 1. The sine and a minus sign will cancel each other out. So the plus sign term that I originally had, that'll now be gone. And I'll only be left with plus sine times cosine squared. And now we're in a much better position because if I split this term by term, I'll have 1 over cosine squared, which is secant squared. I'll have sine cosine squared over cosine squared. The cosine squareds will cancel, leaving me with just sine. So now all I have is really to find the antiderivative of secant squared and sine, and that's easy enough to do. I know antiderivative for secant squared is tangent, and for sine it's minus cosine. Of course, plus our constant c.